Well, hi, this is Matt again, and for our second installment, and I guess really the first thing I want to talk about is a little bit about math. And what I kind of wanted to say first is that I know math can be daunting for a lot of people, and there's been this really unhealthy fear of numbers that probably started for many people from childhood, or this feeling that it couldn't be understood. And therefore, when we talk about things that go into the area that I've worked in for quite some time in computer engineering, the idea of binary can be scary because it doesn't make any sense, right? So I thought, let's step back a bit and talk a little bit about patterns, because patterns are something that we're all used to. And in fact, on a daily basis, we couldn't hardly function if we didn't work according to patterns in some way. Even as a child, when you grew up, when you were just a baby, right? A lot of what you're doing is trying to put together patterns, trying to recognize what is happening and using your memory to see if that is something you recognize happening before, either an event or something being said to you, words that you hear, faces that you see. Your brain is a big pattern matching engine. And, think about yourself at night. You're walking around in the dark, and your brain is scanning for patterns that it can find. What is that thing out of the corner of my eye? What is that thing ahead? Is that somebody I recognize, walking towards me? I'm not trying to cause nightmares here, but your brain is working so much to figure out if what you're seeing is something it recognizes, and that's a pattern. You see those dumb Facebook games, where they throw a bunch of sixes in a matrix, and then you got to go find the 9, right? And your brain is attuned to seeing things, and sometimes even your brain can flip things around and change what you see because your brain is so attuned to patterns that it will fill in where it thinks there are gaps. It'll make it hard for you to see where there are problems or where there's something, not a problem, but something that is different than the pattern that you would expect. So all that to say that math is full of patterns. And so if you can recognize patterns, and you do because you're probably a functioning human being, then you can do math. And in fact, the more that you get into math, the more that you see it, you'll just understand that the patterns are inextricably linked to it. So for example, if you're counting, right, and we think of counting as just 1, 2, 3, 4, but if you think of 1 as just representing one thing, and 2 is 2 of one thing, or basically how do you count one thing twice, or how do you count one thing 3 times? Again, just patterns. And I don't want to belabor this too much, but I think as you see math more, and you might see it through the lens of patterns, you're going to find them all over the place, and hopefully that will make it a little less nebulous, a little less scary. And so, in the name of not being scary, let's talk a little bit about how we think about numbers today. And we have 10 fingers, 10 toes, normally. And so we have learned to count to 10. So we can count, on fingers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I know that sounds like Sesame Street for some people that grew up in my generation, but regardless, you can actually count to, there's actually 11 numbers you can represent on your fingers. Because if you have no fingers being shown on either hand, that's technically 0. So you could make between 0 and 10, which is actually 11 numbers. Because remember, 0 is a digit, and you can count it. But let's just, for the sake of argument, we can talk about the 10 symbols that we use in decimal. So I'm going to write them down here: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, move a little bit, and 10. Whoops, 10. Whoops. Let me back up for a moment. So before I get to 10, this is all done live. I'm recording it, but I'll make mistakes. So you're just going to have to bear with me. These are the digits that we've written down, that I've written down, and that we use every day for doing all of our counting. And it's really, when you think about it, it's kind of nice that I can represent 9 things with one digit, right? I don't have to go and draw 9 dots in order to say there's 9 things, right? And so that's one of the values that we have with using the Arabic system here, is that we can use 9 digits and represent using 1 digit apiece to represent up to 9 things. But then when you get bigger, right? Well, how do you represent 10 things? Well, what we've decided, or what the Arabic system presents to us, is that there's a way to do this spatially. So I've written down from 0 to 9. So if I want to go to 10, what we've said is, well, I'm not going to write 10. I'm going to write next to this column. I'm going to write in the next column over, I'm going to write a 1. And then I'll write a 0 here. And of course, this is all recognizable. What's happening? Well, we've said that this column here is going to be the tens column, right? And what that means is whenever I see a number here, like 1, it's not 1 or one thing. It's 1 times 10. It's 10 things, right? It's like, oh, okay, well, that's nice. But I still want to be able to represent more than 10. They was like, well, great, because this first column is the ones column. All right. Again, you probably learned this in school. So now if I want to say 11, what am I doing? Well, I'm writing 1 in the tens column. So that's 1 times 10, or 10. And I've got, how many do I have in the ones column? Well, I got 1. So 10 plus 1 is 11. Great. So I've got 11 things. So now I can write all kinds of numbers, right? 1, 2, 1, 3, 1, 4. Let's just do this for real. 1, 5, 16, 17, 18, 19, 20, right? And so now we have a way for writing using up to 2 digits. I can represent 99 things, which is pretty convenient, isn't it? And of course, this keeps happening. If I keep going here and I get up to 99 eventually, then I could have one more column. How do I represent 100? Well, I'm all out here. I'm all out of combinations. The 9 to 9 here, I've used up all 99 combinations, actually 100 combinations because of 0. So how do I get to 100? Well, I just move over 1, and I go 100. And so now this third column is the hundreds column. That means that any number in that column doesn't represent that actual number. It represents that number times 100. And the second column still represents that number times 10, and the third column, or the last column here, represents that number times 1. So 1 times 100 plus 0 times 10 plus 0 times 1. Add those together. What do you get? You get 100. Okay? And it just continues on, as you know, right? So we can use this. It's a very compact form to write numbers that are quite large, to represent large numbers. And yet we can do it with just, again, three digits, and up to 4 digits, 5 digits, and it just expands as large as we want. So this just keeps going. And so it's very flexible, right? So, and you can see every column here is 10 times less. So if we get to this column, this one will be the thousands column, right? And this column will be the 10,000s column. And this one will be the 100,000s column. And then finally, the next one here will be the millions column. And so it just keeps going onward, right? Very flexible. Now, with that said, I think you all have probably, again, seen this before, learned it, probably not thought about it a lot because we're just so used to working with numbers on a daily basis that we don't really even think about it. But it's worth remembering because if we're going to talk about a different numbering system and one used by computers today, it'll be useful to remember how this works, to go back to the basics, right? So let's come over and by the way, this here is called, what do we call this? This is base 10. Base 10 or decimal, right? Decimal. And remember the patterns I was talking about? Well, the patterns are interesting because when you get from 0 to 9, you end up looping around in this first column. So this first column will always loop around from 0 to 9, 0 to 9, eventually 0 to 9, all the way up to 89, 90, 91, all up to 99. This first column always keeps looping, right? The second column does the same thing, by the way. The second column will go from 0, because remember, all of these numbers really have zeros in front of them if you want to expand it out. And so you've got 0, you've got 1, you've got 2. Eventually you're going to have these 2s happening 10 times, 3, all the way up to 9. So you can even see from a mathematical point of view, you have these patterns happening. The first column here increments to the total number of digits all the way up to 9, and then it causes the next column to increment, and it resets back to 0. So anyway, little patterns I wanted to just highlight. So we've got base 10, means there are 10 digits that we're talking about, 10 between 0 and 9. Fantastic. Now, what if we had something that was a little bit smaller, meaning that we had a base that was, instead of consisting of 10 digits, only consisted of 2. So again, base 10, we have the digits 0 through 9. What if we had in base 2, we had the digits 0 and 1, and that was it, right? What do we call this? We call this binary. And you're going to see this used, and you probably have heard about it being used in computers all the time, right? So we only have 2 digits, 0 and 1. Does that mean we can only represent, 0 or 1 things? Well, no, right? We have 9 digits, excuse me, in decimal. Doesn't mean we can represent only between 0 and 9 things. We can represent anything. And it's the same way here. So let's jump over to binary and let's start counting. Well, I've got 0 and I got 1. Okay, great. Now what happens? Well, remember, we've used up all the digits in this column. We've counted from 0 to 1, almost like when we counted from 0 to 9. What happens when you go from 0 to 9? Well, you pop over to the next column. So that's what we're going to do. Pop over to the next column and start again. Now we've just incremented, and now this column, this is still the ones column, but now we've got this column. What is this number? 0, 1, 2. Now we're in the 2s column. A little strange, isn't it? Because we're not talking about 10s anymore. Remember here, everything here on the decimal side was multiplying by 10 as these columns grew. You're going to find over here, everything's going to multiply by 2. Okay, very different, but the same concept. So we're going to go 0, 1, 1, 0. We're going to add one more, 1, 1. So by the way, these numbers in decimal are 0, 1, 2, and now we've got 3. Now we've used up both of these columns. What's the next one? We pop over here, 1, 0, 0. That is 4. So that means this column here is the 4s column. So how do we count? Well, remember what we did before? In this column, it's that number times the number here. So 1 times 4 plus 0 times 2 plus 0 times 1. So that means 1 times 4 is 4. We go to 5. We add 1. 1 times 4 is 4 plus 0 times 2. Doesn't matter. 1 times 1 is 1. So 4 plus 1 is 5. And then we go again, 1, 1, 0. Because again, this one incremented all the way to the top, so we add one more over here. So now we got 1, 1, 0. We've got 4 plus 2 is 6 plus 1, which was not there, right? There's 0 times 1 is 0. So 4 plus 2 is 6. And then we go here, 1, 1, 1. Finally, this is like the 99 moment, right? Where everything is going to flip after this one. So we've got 4 times 1, or 1 times 4, plus 1 times 2, plus 1 times 1. So 4 plus 2 plus 1. 4 plus 2 is 6, 1, 7. There. We got 1. And now we get to the next one. 1, 0, 0, 0. And this is 1 is the 8's column. And it just keeps going. So we got 1, 2, 4, 8, 16. This is the 32nd column. This is the 64's column. This is the 128 column. Again, you're multiplying the previous column by 2, doing powers of 2. So you can see here that it works exactly the same way. And you may have to sit down and do this for yourself, but the rules are the same. If you can count in decimal, you can count in binary. You just have to convince yourself that it's the same rules. And so you increment the first column all the way up to as far as it can go for the number of digits you have. And then you reset back and the next column increments. Right? And it's the same one here, 0 to 1. I've used up all the digits. I go back to 0, the next column increments. And then I go, I keep adding, and again the following column, then the next column will increment, and so on. So again, you have to sit down and probably work it out for yourself, but it's not too hard to prove that binary and any other type of base system that we use, it's all going to operate the same way. It just depends on, in the system you're using, it just tells you how many digits you have available. In decimal, you have 10. In base 2 or binary, you only have 2 digits. So now, why is this interesting? Like, why are we even talking about this? Well, you probably know, if you've been around computers at all for any length of time, that somewhere in the underpinnings there's binary, and binary makes the world go around for computers and how they work. Now, why is that? Well, computers don't have fingers, so they don't count the 10 in the same way that we do. Well, I mean, computers don't have fingers, except for the ones that they're building that are robots, but we'll just forget that for right now. But under the covers, under the hood, computers use switches. And if you've heard the word transistor, it is basically a switch. It can be on or off, like a light switch in your room. And so how would you count using switches? Well, it's either on or off. Well, on, if you just count that as a 1, and off, you count that as a 0, or you treat it as a 0, now you've kind of got a binary number you can represent with the switch. If it's on, it's 1. If it's off, it's 0. And because of that, that means that computers can count really well, but they're going to do so in binary. And so it makes it so much easier to think about and to program or to design computers using binary because of that mechanism of these transistors and switches that are employed in the chips, in the chip itself. Now, when you see computers printing on the screen and you're working in decimal, that's because it's doing a translation for you. Eventually up in the programming layer, it's going to convert something to decimal so you can read it out. It's a lot easier to read 8 as a number with using the 8th digit rather than, reading 1000, because we're not used to thinking that way. But under the hood, that's where everything is happening in binary. So I wanted to, again, remind you of how you're used to counting already and how binary is really nothing different. It just means you have less digits to play with. But it's very important in computers, and if you're interested in this area, it's going to help to learn how to count in binary. You're not going to have to, it's not like you have to do a test or anything, but just think about and convince yourself that they all work the same way. It's all an Arabic system. It's just that you're using 2 digits instead of 10 that you have available to you. And so I think in the next time we talk, we'll talk a little more about binary and what you can do with it. But I don't want to get ahead of myself. I want you to be able to just soak on it and enjoy the fact that you've learned binary out of this lesson, and you know more than you went in to this little video. So have a good day and take care.